Welcome back, folks. This is a three-part series on the natural recursive form of a sequence. So it's a series of videos about sequences. Isn't that interesting? I've coined a little phrase here, the natural recursive form, because typically when you do recursive, you will often have variables in the recursive definition that include the n itself, which is called the index value, along with some recursive forms. So what we're going to try to do ultimately is to turn this into a sequence that is in recursive form that has no ends in it. But before we do that, we're going to have to do this in what we would consider algebra or pre-calculus form, which would be the typical form that you would see all over the internet or wherever. I'm going to just start by putting in some numbers here just to give us some values. And let me speed this up a little bit. Okay, so just as we plug these in, you can do them yourself. You're going to get this. You're going to end up with a 3, an 8, and a 15. So these are the values just plugging in 1, 2, 3, 4, and 5 for n. Kind of cutting to the quick here. So in the recursive definition, a sub 1 must be given because that's kind of our spark to get this whole chain reaction going. And then a sub n is going to be having something to do with the previous term. So a sub n minus 1. And then after that is maybe some additional information. And we'll figure out what that is in a moment. So if we're doing that, oftentimes it's important for us to see what happened from term to term. So we added 1 here, we added 3 here, we added 5, and then we added 7, which we immediately recognize as a sequence that is linear or arithmetic. So this is plus 2 and this is plus 2. And because it's arithmetic, you say, oh gosh, this should be pretty easy to write. As a matter of fact, in our class, we often have students that can kind of generate this sequence in their head. Let me erase that a sub n because it's not the same. We'll generate a different one. Let's call that b sub n. And that's this sequence that we see right over here. And many people can just pick this out of the air, 2n minus 1. But if you can't, keep in mind that any linear sequence, this 2 is going to be that number right there. And then, of course, we have to figure out how to generate the 1. If you plug in a 1 for n, you'd end up having to subtract 1. However, this is interesting to note that in the recursive sequence, when n is equal to 2, we have to figure this out so that we come up with the number 1 added. And unfortunately, that's not going to happen over here. So let me see if I can illustrate what I'm talking about. I'm going to erase this box. Okay, I'm going to take this out. And I'm going to write in what we suppose is the answer. I'll put it in green because we're going to erase this in a minute. We're going to add in the 2n minus 1. And let's see if it works. Let me see what happens if we do this. If we find a sub 2 by this little definition, we would get a sub n minus 1, which is, of course, a sub 1, which is negative 1, that coming from up here, the previous term, plus 2 times 2, which is the index number that you see here, minus 1. And notice that a sub 2 then would be negative 1 plus 3, or positive 2. And that is not the answer. That is not the answer we're looking for. What we're looking for is just to add 1. So that's why right over here we have to subtract an additional 2 because we're off by one step, essentially. We're off by one little index or iteration, I guess you could say. So I'm going to go ahead and put that in there and show you how that looks. It's going to be plus 2n minus 3. And that's because we have to be off by 1 in these. We have to generate the 1 right over here instead of the 3. All right, and that's because what you're really plugging in there is an n minus 1, and then you have to subtract the additional 2. Sorry about the background noise there. All right, let's go ahead and figure this out then. So we've got a nice little sequence, and if we went to a sub 2, that would be a sub 1, which is a sub n minus 1 here, negative 1 plus 2 times 2 minus 3, and then negative 1 plus 4 minus 3, obviously then we're going to get 0. And we could continue on down. Let me just do the next one on the side here. A sub 3 is equal to a sub 2, which is 0, plus 2 times 3 minus 3, or 3. And that does match up with the a sub 3 that we have on the other side. All right, I'm going to put a blue cloud around this one because in any pre-calculus or algebra 2 class, that would be an acceptable answer for a recursive definition of this explicit definition. So here's the explicit, and this one is the, quote, recursive over here. But here's what I don't like about it. It's got this n value right there, which is the index number right here. So how does that make it completely recursive? It doesn't. There is a recursive component to it, but it is not completely recursive. So the question is, and this is the big question today, can we write this in fully recursive notation or completely natural recursive? What I call natural recursive would be the way to go. Let's see if we can do that. In the next video, we'll take this same sequence and see if we can get that to work in what's called natural recursive form.